presentation.
Yeah, I've got Runa's right now that I'm saving it right now.
Michael is the other guy who's involved with this. He just promised me to take notes.
I don't know what you're saying. Oh. Hey.
Yeah, I followed the arrow all the way outside. Okay, let's go left.
Sorry. Is this allowed?
Does that pay more? I kind of like the first tennis.
I think we should start.
I'm hoping we close the race.
Didn't you have the sheets in? Did you?
No. No.
I have something for you.
Great. Okay, if you're here for MAPRG, the proposed research group, you're in the right place. We're just waiting to get one more of the slide sets in, and then I think we'll start.
I can also put the slides up on my computer. Just switch it.
I'll just check. I'll just check right now. If it's there now, I'll put it done. Yeah, I still don't have it. So yeah, you want to share? Can you use this?
Yeah.
Okay.
No, but start with your computer.
Yeah, when you have Geo, if you're in for Geo, please.
Yeah.
All right, Miri is passing out the blue sheets. Please sign that. And we're ready to go. So this is the measurement and analysis for protocols proposed research group. This is our second meeting. This is my co-chair, Mirya Kulovind, and I with ETH Zurich, and I'm Dave Plonka with Akamai. We're going to start off with, well, first, the IRTF has the same IPR right statement as the IETF. So if you don't know what this is, go read it. If you think you have IPR issues that you don't want to disclose according to these terms, then consider not being here or talking to your legal people about how to make that work. This is the agenda. For the first part of this talk, the proposed charter is at this URL. That stayed the same since the last time. I'll give a little summary of the charter here because we're a new group and I'm expecting maybe a lot of you haven't heard that before. We have a mailing list to talk about the topics of the research group. Today's slides are at this URL. The meeting's on MeetEcho. There's audio streaming. There's Jabber. I think Maria said we have a scribe or we have someone to do the minutes. Is that the case?
Yes, thanks to Michael Balsam.
All right, thank you.
Minutes. I can.
So the agenda for today is, and we have a really tight schedule, which is good because so many people are interested in presenting. So there's almost no spare time at all. So please excuse me if I interrupt you or whatever. We're going to go in about these 10 and 15-minute blocks with the different presentations. First, we're going to start with the introduction and overview that I'll do. And then Leslie Daigle is going to talk about a similar activity that's operator focused that she's working on called NOMA. Then Philip Richter from TU Berlin is going to present some of his most recent work about perspectives on studying the active IPv6 or IPv4 address space. Then I'm going to do a short presentation about a 16-year study that I've been doing on what I'm calling Internet of Things from back before there was that term. Then Giovanni is going to talk to us about this Anycast versus DDoS work that he's done recently. Varun is here from callstats.io to talk about WebRTC measurements. Johannes Klick is hopefully here. I think I've talked to him. Is he here? Yay. He'll present some of his recent work. Tommy Pauly from Apple has a presentation about a view through API eyeballs. And then Runa is going to talk to us about some recent work they did, DSCP and EvilBit. And then I think the open discussion, we probably won't have any time for that. We'll try to use the time in between the talks to fit in a few questions if we can. So the proposed charter, I won't go through the details of it, that's online, but a short summary of it is we're really meaning to do two things in this research group. Discussion about measurements and techniques that would inform the development, deployment, and operation of existing protocols being defined in the IETF or have been defined. So really just measurements that are specifically targeted to helping people that are also meeting here with some of the things they're doing so they have a direction or understand why protocols do and don't work or how they're working. And then the second is to just propose measurement results about the same thing. So how you would do the measurements and what the measurements are. The only thing that we're kind of at this point trying to exclude is things about measurement infrastructure, formats that use to carry the measurements. The sort of logistics of it is currently out of scope. And the expectation would be if something's going to be presented here, we should be able to easily map it to an existing effort in the IETF or identify the existing protocols that it relates to. And then we're meaning to foster introductions between people and collaborations. So a couple of the topics we'll touch on today are about that, not just presenting work that's done and completed, but also ongoing partnerships, which we've not had many yet, but that's one of the efforts. So we're going to finish up the introduction by the IETF had the Applied Network Research Workshop meeting this past Saturday, and Miria identified, in this case, 6 works that were presented there that were all pertinent to this. I don't have time to go through them now, but they're in this initial slide set. They're in the meeting materials. Those might be ones that you particularly want to hit. And then because we had so many people requesting slots at this meeting and we ran out of them, we have a little ad in here for a work that Roland's doing. So I invited him to give this one slide. So this is really just an advertisement to invite you to, if you operate a country code or some other top level domain, they would like to work with you to do this large scale active DNS measurement. And Roland's here. If there's time at the end, you can talk to him. Right, there he is. But those 7 pieces of work are all certainly pertinent and would have been candidates to present here today. So next up is going to be Leslie Daigle talking about NOMA. So I'm going to pull that slide set up.
That worked well. I destroyed it.
All right. Okay, well, thank you. Network operator measurement activity is something that I'm doing as part of my little company. And the tagline for the tech arc work that I'm doing is basically better networking through collaboration. So I think it does indeed fit in with what the proposed RG is talking about. And this particular bit of work is something that I'm doing in collaboration with network operators, one of who's actually going to step up and do part of this talk, so you can see that it's not just a meta-level discussion. So the objective of the network operator measurement activity is to form up a collaborative industry activity to share some measurements of network function. So these are measurements done by network operators themselves that they would contribute to share a picture of the overall health of the internet. The basic premise is that it would be useful to have some of that perspective, some of the in-network perspective, to get an overall picture of how the internet is doing, focusing on V6 first because it's emerging, because we can look at a basic measurement of V4 to V6, a ratio of V4 to V6 round trip times as a reasonable metric for seeing how networks are performing and how V6 is evolving. So that's something that I and others who care about the internet health care about much more than the specific operational details of any given network. And the premise is that doing this sort of thing can create a target for new operators, e.g. in developing economies, to know what good looks like. You know, is what they're doing actually worldwide class standard? Is it not? And I think that's true for V6 deployment in general. And it's also an opportunity for networks to become a little bit more, network operators to become a little bit more objectively introspective. So, well, great, what's in it for operators? I think that part of the point of this is that self-instrumentation is useful. Self-instrumentation may seem obvious, but apparently it's not. And by doing some of the self-instrumentation, just some simple RTT measurements set up from within their network looking outside, it gives concrete operational guidance about which John can say more. This is stuff that is at a level of detail that I wouldn't care to try to extract from a network, but again, when we talk about trying to get some shared information that gets put together at a trusted third party to create a picture of, you know, what is a summary view of the overall state of things, we actually have existence proof of this sort of thing working. In the World IPv6 launch that was hosted by the Internet Society, Google, Facebook, and Yahoo actually provided the Internet Society with some perspective of what they saw of accesses coming from the participating networks. So Google, Facebook, and Yahoo sit in a particular point of the network so that they can see, they know they know which traffic coming from what networks is coming over V6. So they can present a summary view. This is not operational data that they can generally share, but shared with a third party, a trusted third party, and put together, you can create a useful map. So that work is ongoing, and is, as I said, a good existence proof of this type of approach. So getting a grip on V6 deployment, I really want to say, just emphasize again something this room probably knows pretty well, that what you see of V6 deployment depends very much on where you start to measure it. So the World IPv6 launch had has the content provider perspective. Network operators see it from a very different perspective, and I think it's one that's useful to share in terms of creating a view of the overall deployment of V6. So John.
Thanks, Leslie. John Brzezinski from Comcast. So, Dave, how much time do we have here?
I'm sorry?
How much time?
You've got 10 minutes.
Okay. Plenty of room to be sloppy and self-governance here. So, okay. So, roll back a few years in history. Folks that I work for said, hey, sure, go ahead and roll out V6, just don't break anything. It's like, okay, no problem. So, and I feel like I've told the story to a number of people, so I apologize if this is a bit, for those of you who've heard this before, but it's easier said than done. And frankly, it wasn't entirely something that we were doing. We were doing some of it in different parts of the network. So 9 months before World War 6 launch, we went ahead and basically, kind of built what we thought was basically like a canary in a coal mine, trying to make sure that we had all the right measurements in place across the network so that if something broke on the internet, we knew about it before our customers found out. That falls into a number of categories, everything from us doing something wrong, which, nobody's perfect, to, something else going wrong across the internet ecosystem, right? Again, nobody's perfect. And while a lot of people who use the internet think that, everybody is talking to each other on a daily basis, it's not always the case. So a lot of this for us was to make sure that we basically had eyes on how the customer experience, right? And all the underlying kind of, technical bits to go ahead and do that. The approach that we inevitably developed is one that we ran from the core of our network, which is intended and expected to be extremely reliable, right? Predictable, I guess, is the best way to put it. A lot more uniform, right? But the same approach has equal applicability to just about any aspect of the network. Everything from the core data centers to the access network, and even within, to and within the home. So what we ended up doing is we built a platform. I kind of did a little bit this. I kind of probably could have done a better job with the slides here, but a little last minute nature of kind of the activity. So if I had a picture, what I'd show you is our backbone and kind of like all these regional networks connected to it. The United States is pretty big, and we kind of go from coast to coast on it. So, there are very different experiences in Boston or Philly compared to Seattle and San Francisco. So we thought it was important to be able to run this instrumentation from all those parts of the network to each part of our own network, and of course, to the internet. For the past, how long has it been? 4 years? 4.5 years? There are some measurements that we've been running every 5 minutes for the past, 4.5 years. And we'll tell you a little bit more about that here in a minute. So what else did I intend to say? So we have basically a centralized kind of database of sorts of targets that we want to measure to, whether they're on the network or on the internet. And of course, we store all that data so that we can kind of go, look back. I'll give you a perfect example. My good friend Paul from Facebook, when I was at his office, probably a month before World War 6 launch, he said, "Hey, let's try this thing out. Let's give it a go for real." So Paul was like, "Hey, we can turn on Chicago. I can send, Chicago Comcast customers IPv6." I said, "Okay." So I logged in, made sure that I had kind of my instrumentation set up, and he turned it on. We went to dinner. Came back an hour later and said, "Oh, hey, wait, time out. V4 is being served from like Detroit, and V6 is being served from Seattle." So we said, "Well, we should probably turn it off and fix it, and then turn it back on, right?" But so it's a pretty simple but powerful illustration of kind of why we did it, right? And it served. We had tons of mileage out of it. Turns out these days it's more than just kind of tactical use like that one. We use it to really kind of start to do things like comparing and contrasting V4 performance versus V6. As we all know, V6 adoption is really kind of moving along quite nicely. But over the next few years, and even already now, V4, the properties of V4 are beginning to change, right? Things like address depletion are kind of really advancing the availability of carrier grade NAT. So some of the measurements that we did, just one example is, we use something as basic as libcurl. With libcurl, you can build a nice little simple probe, run it basically anywhere, and collect like very simple attributes like DNS lookup times, TCP connect times, and download and transfer times. And we basically kind of did this to arrive at what we call it like a customer experience index, right? Like in the sense that like when a customer, and we used HTTP because, let's face it, folks, it's pretty widely used protocol last time I checked. So we thought it was a better representation of kind of really exercising the the ecosystem end to end. So we would do take an entry from the database, run a V4 and V6 test, and then collect those attributes every 5 minutes for the past 4.5 years. And we find a lot of very interesting things about that. Another side note, at one point we were doing some DNS server, upgrades, and we were getting some phone calls in from people who were using Android telephones. after like the Lollipop upgrade where it started to support DNS every 6. Well, it turns out we had pushed out some configs to DNS servers that were not working right. And that's the reason why we were getting the phone call. So another like Paul Facebook example, but it was one that was really internal. So we were able to find that with this tooling, we were able to find when we make mistakes, right? Fortunately, we found it very early in the process. We fixed it, and we avoided anybody from even really noticing. So
3 minutes.
Oh wow. Okay, I better talk faster. I actually talked about this one already. The overall kind of plan was to just build something very simple that you can run it on big honking server or a little teeny cable modem or even your computer in between. And it's extensible so that you can add other types of measurements. I just happened to discuss for you today the one that is HTTP based. 4.5 years, every 5 minutes. We even, some of the other measurements are oriented around pings and trace routes. We do some DNS stuff, and that's it.
So I just wanted to wrap that up back into the NOMA project. So we held an invitational workshop in June. There were half dozen operators there. John did have pictures. The other operators' eyes lit up. So I think there's interest for doing some of this kind of measurement internally and potentially some interest in actually doing the kind of sharing that I was just describing. So there will be a published report from the workshop we had. Hoping in terms of moving forward, hoping to leverage and share the Comcast experience, and then get some agreement among operators on an initial set of, a template of what to measure and how to do this and how to turn it into something that at some future point we can be talking about actual results from the NOMA project. So that's what I had.
Lars Eggert, while you talk to the operators, ask them if there's a way to make the data available.
What was it you said, Lars?
So the question was, basically making the data available for other researchers who want to do deeper dives and their own form of research questions on the data. I think that's an interesting and onward discussion. I think the first point is just to try to tease out some of that data for any kind of public consumption.
So if I get it right, at the moment this is going to be like workshops between operators, so it's like a closed community and they share their measurement data amongst themselves and sort of learn joint lessons?
No, so the closed workshop is to get operators interested in doing this and used to the concept of possibly sharing some vision of it, some version of it to a neutral third party that would publish it publicly. There would be a public view on the shared data. Otherwise, it's kind of people talking to people, and why am I talking to you about that?
Okay. And did I sort of gather that you're going to try and come up with like a sort of BCP about how to do measurements of the network and maybe some tools that are publicly available for other operators to use? Or
Yeah, I think we wrote something like that down. We went to, I get a demerit for my internet draft refresh rate here. So we did it for the last IETF, wherever that was, and we had a LMAP draft that we did that we have to split into basically 2 different drafts. But we did start to write that down, at least from Comcast point of view. I mean, it may not be right for everybody. One of the things that we are looking at doing, I've been talking about it for a while, just no time. We even talked about like open sourcing some of the stuff that we did. Like I said, we're not splitting the atom by any stretch of the imagination, but it's, from what we've heard from people, it would help, right? It helped jumpstart somebody else trying to get going, right?
yeah, I mean, from the sort of like in IPPM, we've talked about having a registry of tests that you do. So I kind of think that's a good idea, but to be able to standardize all of those tests is kind of a long-term activity. So being able to have something which is sort of an intermediate step where you've got tests that are kind of, you can sort of start agreeing what common tests are.
Yep.
And eventually we get to an IPPM standard. I think that'd be
Before we get
a
hooked
cool
here, one of the things
anyway,
that,
I like measurements.
before you get hooked, one of the things that we commented on in IPPM or LMAP in wherever we were last time is, I think you should insist that a reference implementation for all those measurements be included with their internet draft or what have you. I think that's a pretty important step.
Yeah, and my last comment is that this is not meant to be a be-all and end-all, but rather complementary to a lot of the other excellent work out there.
Thanks, Leslie and John. Again, I apologize. This is really tight today. We have 8 presentations, so just so that everyone gets the same amount, I'm going to interrupt you. If it doesn't work out well, we'll do less next time.
Okay.
Go ahead, Philip.
Okay. Hi. My name is Philip, and I'm going to present you some bits and pieces of our newest work, which is called Beyond Counting: New Perspectives on the Active IPv4 Address Space. This is joint work with George, David, and Arthur, and it's currently under submission. But you can get a preprint under this archive address here. You're all aware of the IPv4 address space exhaustion. So just as a really quick introduction, IPv4 has been around for like roughly 35 years. It gives us a theoretical maximum of 4.3 billion available IP addresses. The problem is that IANA, which governs the address space, ran out of addresses in 2011. And in the subsequent years, also the regional internet registries ran out, which is shown here in this left-hand figure. And so today we face a situation in which only less than 2% of the globally routable address space is still free and unallocated. Now this has, of course, caught the attention of the operators community. Just to list some of the efforts also here in the IETF community, there's a lot of work on IPv6 transition mechanisms, there's work on IPv4 multiplexing and address sharing mechanisms, and more generally, efforts to conserve IPv4 address space. And it has also caught the attention of internet governance bodies who currently establish transfer policies to transfer address space, and also to provide the right incentives to increase address space utilization. It also caught the attention of the academic community, in particular the measurement community, with measurement studies that somehow try to answer the question where we are right now, which boils down to the seemingly simple question of how many IP addresses are actively in use, or what fraction of the address space is really in use as of today. And there are 2 recent works in this field, one from 2014, which used a bunch of active and passive measurements, and on top of that, a statistical model to finally provide the number that currently, or in 2014, there are 1.2 billion IP addresses actively used. There's a second work that also used active and passive measurements to finally measure activity from 4.5 million /24 address blocks. The challenge here is that there is really no single vantage point that can capture all this activity. And that motivated us to ask the question, what can we say from the CDN's perspective? So how much activity do we see? And also, can we do more than just counting IP addresses? Can we find out more about somehow the nature of address activity, and also about the utilization potential within already active address blocks? And for that, so the foundation of our work are logs collected at one of the largest CDNs in the world, which operates more than 200,000 servers and 1,500 ASs and serves about 3 trillion requests on a daily basis. So what we have in our logs is that whenever a user requests an object from the CDN, we see the IP address and the corresponding number of objects that were fetched from the CDN. So just to give you the totals for 2015, we indeed see 1.2 billion active IPv4 addresses, also confirming prior work in this field. And if you break it down to /24 address blocks, we see 6.5 million of them active. Now, as the first thing, what we did is that we compared our visibility to what we can see in with active scanning campaigns. In order to do that, we used 1 month of our logs and compared it to a bunch of ICMP scan snapshots from the ZMAP project. What you can see here in this bar plot is first that there's a large portion of addresses that we see in our logs, but they are not visible in ICMP scanning campaigns. There are good reasons for that. The first is that a snapshot view will naturally not capture the activity of hosts that are just active for a very short period of time. And secondly, that there might be a lot of hosts behind firewalls or nets that just do not reply to an ICMP request. There's another interesting portion here, and that is the right portion towards the red portion in the right of this plot, and these are roughly 8% of IP addresses that we see in active scanning campaigns, but we don't see them. We don't see activity in our CDN logs. And we have more details on that in the paper, but the majority of them is related to serving infrastructure and router IP addresses. Now, these were the totals. Becomes a little more interesting if you have a look at how this has developed over time. So what is shown here in this figure, going back to 2008 on a monthly basis, just how many unique IPv4 addresses did fetch content from the CDN. And we see this almost perfectly linear growth for these many years until 2014. And in February 2014, we have this relatively abrupt stagnation in terms of unique active IP addresses that we see on a monthly basis. And now that really motivated us to study what is happening now within this seemingly constant set of active IP addresses that we see month after month. Now, what I show you here is going down to a daily basis. Like on a daily basis, how many IP addresses do we see active, which is the blue line on top. And so we have some day of the week effect, but generally also like seeing it on a daily, seeing activity on a daily granularity, it looks relatively constant. But what we show in addition here in these bottom lines are the up and down events. And so we just define an up event in the sense that an IP address was not active yesterday, but it's active today. Correspondingly, a down event means an address is active today, but it's not active tomorrow. So when looking at things on a day-to-day basis, there's around 7% of address churn. And then first we thought, okay, this is just a short-term thing, so let's aggregate our data set into larger time windows, and then probably this churn will go away. But actually what turned out is that when we start comparing weeks to weeks, so basically we take the union of all active IP addresses within a week and compare it to the next, we also see a churn of roughly 5%. And basically for any aggregation level, we tried it up to 1 month, we see a constant churn of IP addresses. So meaning that the number of active IP addresses has stagnated, at least from our vantage point, but the set of active IP addresses varies on all time scales. Just to show you what this does in the long term, so what we did here in this figure, that we take the first week of 2015, we set that as our reference week. And then for each subsequent week, we plot the number of IP addresses that were not active in this first week, but were active in later weeks. That is shown in the positive direction. And correspondingly, also we show all these IP addresses that were active in the first week, but were not active in subsequent weeks. And so basically after 1 year, we can see that almost a quarter of the active population of IP addresses has completely exchanged. Now that got us really curious into what might be some of the root causes for this heavy churn in active IP addresses. What we did in order to study this, that we created what we call an address activity matrix. So basically we take all the address space and we sort all IP addresses. As you can see here, we create this matrix, and as we have the logs that for each day show us activity for each individual IP address, just whenever we see activity, we draw a green dot in our matrix. And actually, so then we generated this matrix and we started scrolling down this matrix and looking at it, and we found a bunch of really interesting activity patterns, and I want to show you some of them here. So the first set of patterns is what we term in situ address activity. So why do we call it in situ? Because from our perspective, the churn and the activity that is seen here is the result of the address assignment practice in a specific block in conjunction with the user behavior. So these address blocks don't show any sign of that, for example, an operator took a block into use or took it out of use. So this is just an address churn that we see as part of its regular behavior. Like, for example, the block in the top left, which is a statically assigned address block where we just see a few active IP addresses, and they show a day of the week pattern. In contrast to that, for example, in the second, on the top right, we see a DHCP pool. And already we can see that just this in situ activity causes a lot of that perceived churn. Of course, we also see patterns like this, where it's relatively evident that there was some sort of operational change, that the behavior of an address block fundamentally changed during our time window. Now, to give you a glimpse of what this activity matrix looks like at scale, I hope that you can see that right here. So this is 20,000 adjacent IP addresses within active/24s. So we only look at active, where we see at least one active IP address within a university network. And here we can really see this huge breadth of different activity patterns. We see a lot of incarnations of dynamic address pools towards the left. And then we see other address blocks that are just very sparsely populated. And we also see other things like, for example, as this is a university, we also see the beginning of the fall term. Now, so we found this matrix really insightful, but of course, like scrolling down this matrix and looking at it doesn't really scale. And that's why we introduced some metrics to capture utilization as seen in this matrix. The first one is the filling degree per /24, which basically just means we take the address space, we divide it into /24s, and we just count the number of active IP addresses that we see within an address block. And for that, we consider our 4 months, a 4-month window. So meaning if it was just one IP requesting one object in the entirety of 4 months, we count it as active. In these two examples, of course, we see the left one has a rather low filling degree, and the right example has a really high filling degree. And now, if you look at the entirety of the active/24 blocks, around 6 million that we see, and we see this. And so basically, what it means is that there's only about 40% of the active address space that we see for which we have a really high filling degree. And for almost 60%, we see a lower filling degree. And we identified one possible root cause for this, and that is basically the type of addressing used for an address block. So what we did is that in order to get these 2 additional lines, that we use reverse DNS PTR records to tag some address blocks as being likely statically assigned or dynamically assigned. And these two additional CDF lines just show the filling degree for these 2 subsets that we identified using reverse DNS. And here we see that those address blocks that are tagged as likely statically assigned, I mean, there are some flaws with this using reverse DNS for this, acknowledge that, but for those address blocks that are tagged as likely static, 70% of them have a really low filling degree. On the other hand, we see that for dynamic address blocks, most of them show a really high filling degree. So, well, and this means that there's a lot of unused potential because a lot of address blocks just have this really low filling degree, and the other IP addresses are likely not in use. Now, focusing on the dynamic address blocks, just having this metric of the filling degree tells us that the utilization is really good in these address blocks. But of course, dynamic addressing also doesn't always result in the same level of utilization, as you can see with these 2 examples. So these 2 are both address blocks that are dynamically assigned to hosts, but visually you can see that the utilization is really different for these 2 minutes. Okay, and in order to capture also that, we introduced a second metric, which is the spatiotemporal utilization. So basically we look at this and we take the red portion and we divide it by the maximum possible utilization. And what I just want to show you, focusing on those address blocks that really have a high number of active IP addresses, so they are likely dynamically assigned, and we look at their spatiotemporal utilization, we see that the majority of them indeed shows high utilization, between 80 and 90%, but also there's a third of them that are likely dynamically assigned, but they still show really a relatively poor utilization. Okay, so that was it from me. We have more stuff here in the paper. This is an old slide set. So we have more about that in the paper. And so yeah, okay. So we provide this comprehensive study of IPv4 address activity, and we provide some metrics that go beyond this binary notion of activity of an IP address. And we hope that our work, and possibly also our metrics, if other people would adopt them, can inform network operations, and in particular address assignment practice or even address reassignment practice, and can also be fruitful for security appliances, like for example host reputation. Okay, with that I conclude.
Thanks, Philip. I think we have time for one question. Someone? Go ahead.
It's Dave Dolson. I think the visualization is interesting, but this is collected at a CDN, correct? I wonder if you tried to account for some blocks that may never try to contact your CDN. Like, for example, other people's servers would never initiate connections. I wonder if you tried to account for that at all.
Of course, we are limited to the CDN's perspective. What made us quite confident that we capture a large portion of the active address space is that when we compare ourselves to ICMP, that the fraction of IP addresses that are visible within ICMP but not visible in our logs is comparably small. But of course, we would need other measurements to extend it also to the server space.
Okay, I'm up next. I'm not in my chair role, and for the beginning of this, I'm not even in my Akamai role, because I'm going to talk to you about a measurement study that I did about 16 years ago, and then we recently revisited to try to get an idea of the lifetimes of devices such as the Internet of Things sort of devices. So I'm calling it's basically the MAPRG portion of our efforts for the Internet of Things. So basically in two parts, I'm going to first go through this case study that we wrote a short position paper that has the measurement results in, and also some thoughts that Elisa Bosky and I prepared over 10 years ago that I think, at least I find them still relevant or still as confusing as it was 10 years ago. And I think it's illuminating to see that we really haven't gotten very far with this sort of thing since then. And then we'll talk a little bit about the IAB sponsored a workshop called IATSU for Internet of Things Software Update. That just happened last month in Dublin. The report isn't written up yet, but one of the things we did in it was a short unconference portion where we just talked freely about new topics. And the one that Daniel Thomas and I chose to talk about was the idea of what kind of measurement analysis should we be doing to get some idea what's going on with IoT. So first, a case study. This is about Netgear SMTP clients, Netgear devices. This is before Cisco acquired them, 2002, 2003. Who here knows what this is about? Okay, so this is really good. Only about 10 people have hands up. So I won't be completely boring you. So this was, I wrote a web page called Flood Routers Flood University of Wisconsin Internet Time Server in 2003, and it got slash-dotted, and for a few years we were working on this issue. And I said, then we've recently updated the measurements. So this is the kind of devices it's about, and these are sort of stand-ins for IoT devices. So these particular 4 models of Netgear pieces of equipment had this curious thing that they use this simple network time protocol. SMTP is the simplest form of NTP. You just send a packet out and you get packet back with the time. There's no stateful aspect to it. It's just for really like a simple device to get the time. The curious thing about them is they were hardwired to use the IP address of a time server on our campus. And they were probably this was probably done by someone who wrote the low-level firmware very early on, and somehow they didn't notice that it was hardwired to use that, and they manufactured many hundreds of thousands of them and shipped them all over the world. So in bold, I have, when we worked with them, they did some code updates, but you can imagine without a software update mechanism that's automated, how are you going to update 500,000 devices in the field? And so they don't get updated. So we have an opportunity to see what can happen with devices that are hard to reconfigure and actually are quite old today. So why is this IoT? Well, my sort of twist on, a lot of people don't have a definition of what they think IoT should be. You know, is a smartphone an IoT device, or does it have to be like something like a washing machine or something that has internet connectivity? What I think is interesting about them is that the devices are homogeneous in their configuration, they're rapidly designed, manufactured, and deployed, and they depend on the internet. The difference is they depend on the internet. Certainly you could have had a little device like these Netgear devices that could go on any network. But the difference was these relied on something that was in the big I internet. They weren't just a networking device, they're an internet device. And then the other observation I want to make is we're not usually informed about the arrival on the internet of new classes of hosts, right? We kind of trust that they're going to be pretty good. But because these can be deployed so quickly, it really presents a severe potential problem for performance in the internet, reliability, and the security challenges that a whole bunch of homogeneous devices showing up immediately can present. So this is the historical part. I'm going to spin through this hopefully a little quickly, but as a network operator circa 2003, this is what I saw on our traffic. We saw this huge spike in traffic. This looks like a typical denial of service attack at the time, so my job was to go and find what that was and probably block it so it doesn't damage the campus network. It did damage the campus network. In fact, it caused the outage that's shown in the white space there. The packet forwarding rate was just well over double in very short order. The unusual thing is this doesn't rise as just a straight edge up. It kind of goes gradually. And that's sort of a hint as to what was going on here. I just thought it was a random source address denial of service attack, so I blocked it. So that was in May. And about June, I'm looking all over my MRTG RRD files, and I said, well, find the files that are the most active. I just want to know what the most active interfaces in my network are. And it turned out that this firewall filter was the most active thing. It was blocking 250,000 packets per second. And it had been going for 4 weeks or something by this point in time. So a huge denial of service of flood. Unfortunately, from about 700,000 discrete sources, real sources all over the world. And you can imagine I was looking at a trace and I just thought they were random addresses. So I started looking, well, they're not random across 1 billion addresses or 2 billion. They were these predictable certain number of devices. So what I started to do then in 2003 on the left, this is just a bigger version that in 2006 on the right, is to count every day the number of source addresses that were producing these kind of queries. And the curious thing is they use a specific source port. That was the key to being able to understand what they were. 23457 is the source port they always use, so I just counted all the NTP clients that were using 23457 and hitting us. And so what we're seeing is a birth rate on the left side of these devices having been manufactured, being in the supply chain, getting out in the retail market, getting deployed in networks like Deutsche Telekom or whatever. And then you're seeing this decay, which is their death, right? And this is over a period of about 3 years. So people started to say at the time, well, what is the half-life, Dave, of these devices? First, maybe they have this kind of exponential thing. And it looked like, well, that would just kind of curve off and have this long tail. So I said, I don't know, maybe it's some hundreds of days. So 10 years later, I left that role. I'm doing different things now. Some awesome person 10 years ago set up their mail server to send them an email in 10 years to ask me what was still going on with that. That's absolutely what happened. And it happened a few weeks before the IATSU workshop. And I said, I bet I could find that with the help of my colleagues at the university. So we did that. And this is the port numbers. These are the port numbers that we see. It's going a little slow because of scatter plot. So these are the port numbers on the horizontal axis that we see hitting the time server, and the number of unique source addresses we see in a day using that port. And I've highlighted and I've circled in blue that dot. So you'd be like, well, does that mean anything? It looks like it's in the middle of a whole bunch of noise and stuff. Maybe there aren't any of them anymore. Okay, and so when I zoom in on that, though, however, we see that there's the clients have an affinity for using these port numbers as sources that are divisible by 1024. But that one is a really weird one, 2, 3, 4, 5, 7. It's a little bit off. That's too high. So now I know those devices are still out there 16 years later. Okay, and we can use the adjacent port numbers as a baseline to know how many to subtract. That someone would just be choosing that. So here's what we get. On the very right, over here in 2016, I counted some, adjusting for the baseline, some 3,300 of them seem still to be out there, where we were up at a peak of 700,000 in circa 2004. And then I did some really naive projections. If it was a linear, if it was a linear decay, that's where that sort of dotted line goes down. This whole thing would have been over before 2009, but it's clearly not. If it was an exponential decay with a half-life of 590 days, you can hit that point out there, but that's not right either, because you see it drops quicker than what we saw. So it's not a base 2 exponential decay. It's not certainly not linear, but this is the only real measurement I know of the lifetime of a device on the internet across something like 16 years. I'm sorry, I had a bigger version of it. I could have showed you that. So now let's switch to, that's the measurement study. I don't know of any other IoT-based measurement studies out there. If you do, tell us about them. So now the new ideas for what should we be doing about IoT? What I just asked about was, does anyone else have real counts of these things? At the IATSU, there was one person from Electric Imp that they said they had more than 500,000 of the devices deployed, and they've upgraded them remotely in the field. That's the biggest successful remote update for IoT sort of devices that I know of. Who are the stakeholders for measurements about these activities, right? There's a lot of them, and we'll visit these in the subsequent slides. What kinds of measurements should we do? What are the privacy and anonymity issues, right? If your Tesla car or something is an IoT device, do you want everybody in the world to know you have a Tesla car parked in your garage or something? And how does IPv6 fit into this? So in the case of the counts, we had 700,000. In that case, I said the Electric Imp one was 500,000 successfully updated in the field. Let us know if there are any others. Stakeholders. Well, the manufacturers certainly are, because they have no idea once they push those things out when they're actually turned on. They had no visibility to it. We had visibility to it, not the manufacturer. So that would be key for the manufacturer to be able to know. A service provider, now the service providers that are running the networks where these devices are in, they would want to know this. But also there's this notion of, in fact, Electric Imp does this, sort of IoT as a service that helps you run your IoT devices. They would want to know these things. So how you could manage that and do risk assessment, and maybe that's an attractive product, bundling the service about how to manage the IoT devices with the devices, the physical devices themselves. The standards organizations, of course, why we're talking about it here. They'd be interested. Vendor consortiums would. What's trending? What kind of IoT products are out there? And researchers like ourselves. Regulators, governments, and lawmakers. It's very possible. It's not attractive to a lot of people, but it's very possible that this is going to have to involve some sort of risk management insurance, and maybe they will get involved there. So then lastly, the user owners and customers of the devices. What if we have 100 of these in our home, and you just want to even audit your own home? What am I still relying on? What's in my walls that's giving me the ability to turn my lights on and set scenes and things? If you want to sell your home, does the buyer need to know what IoT devices are in it? So then let's switch to the kinds of IoT measurements. The ones that now this is in my Akamai role, the things that I'm thinking of doing. As the CDN, we see these devices sometimes come to us. So the World Wide Web user agent strings, that's a really interesting way of looking at it. We see many tens of thousands of user agent strings come to the platform. And sometimes they identify things like certain brands of televisions, or I added the IPv6 clients to their IPv6 clients. Sometimes they expose the manufacturer of the NIC that are in there, so you can get some real counts that way. And then what requirements or methods would we have for determining the authenticity of this, right? Because if I'm relying on something simple that's just voluntarily given to me, well, that could certainly be spoofed, like the user agent string. The same way you spoof it to pretend that your browser is some other browser so that you can get the content that you want. We want to measure the volume of traffic. In this case, there was 1 packet per second from all these different devices. I didn't go into the details to find this the URL there, but in their failure mode, they sent 1 packet a second. Well, clearly, all IoT devices will be able to send a lot more than that. So do we care about the volume of traffic that they put onto the internet? And what if they're synchronized? What if right now we have this issue with smartphones, for instance. What if they try to synchronize their update? And you could have billions of homogeneous devices. Another kind of interesting thing to measure is just the raw uptime of it. One of the proposals that we talked about in the workshop was, well, should the device have a lifetime? And maybe not that it goes completely dead, but it quarantines itself or something. Well, these devices, even without a real-time clock, they can count the number of cycles that they've run, as long as they've got some kind of persistent storage, and they could count their lifetime, go into a different mode until you updated them and continue on from there. But presumably, you guys can think of other kinds of IoT measurements that we might want to talk about in this working group or pursue in our own endeavors. The privacy and anonymity portion, we talked about this a lot. I think hopefully this is an interesting portion of the report that we have. But the requirements for this differ severely by stakeholder, right? If you're the manufacturer, you want to know it. If you're running them on your network, you might want to know it because you're trying to help your customer operate them. But if you're a user, you don't want people to know what kinds of products that you bought. We mentioned things like version number homogeneity. You would like to be able to somehow audit the devices out there and know what versions of code they're on. But just being on a different version of code makes you stand out. So if that's something that's visible externally, that might disclose something about you that you wouldn't want to. Or maybe it means that you're on an older version and it's somehow vulnerable. Miria, could you hit OK on there? This is the way I guess Symantec wants to advertise their product. So then lastly, from the privacy measurements, what would we say is demonstrably private? K-anonymity, this sort of thing that they use with medical records. How can you tell that you can't tell which one of those patients that record is from? Could we use something like that in IoT? And then lastly, we talked about some things like sketches about how you could use maybe suppress through the DNS hierarchy reporting, so you'd know approximately how many devices were out there, but we'd not necessarily know which specific addresses they were at, so they wouldn't be vulnerable to being taken over or being attacked. And then lastly, the IP6 aspect. This was really concerning to me. In this meeting, the IoT vendors that are selling stuff today said their customers don't care. And so probably means we can't leave it to the customers to decide whether or not you're going to have IPv6 on them or not. And then we're seeing devices now, and John Brzezowski has told me this, we're seeing devices that say they support v6, they get a v6 address, but because of like happy eyeballs, they never use them. So if we don't get over on top of this with IoT, and all these things are using IPv4, it's really going to cause this floor that we can't drop below for how many devices no longer use v4. And that's a particular interest to me, and I'd be interested in working with someone on that if you want to pursue that. So that's all I have. If you have any comments or questions about it, do we have any time, Miria?
Yes, I think we have like 2 minutes.
All right.
I'll ask a question here too. Dave Dolson. So you're talking about like privacy and all this, but on the other hand, you found it very interesting to have that source port that you could use to track. So, if the network's being flooded and we want to say, oh, there's a bug with something, your house is sending the stuff. How do we figure out what device it is if there's no signature? So I wonder if you've given any thought to, should IoT devices somehow, tag their traffic so that you can track down which one is buggy?
We did. I think I'm just going to collect the thoughts instead of saying what I think about this. But,
sure.
But thanks.
Well, I have the flip side of that question. Christian Wiedemann from Microsoft. We are working a lot on the privacy of the internet. And one of the things we are doing is basically using encryption and also reusing as much metadata as we can from the packets. So isn't there some bit of a tension there? Because, I mean, if I really strip my metadata, you won't be able to tell this is this or that.
Yeah, and I think it deserves some kind of design attention. Are there modes of deployment for IT devices where you want someone to know what they are, and maybe only want your service provider to know and no one beyond that? So yeah, but I mean, can we do these statistics in a way that preserves privacy? That's a great question. I'm just going to leave it as a question.
Lee Howard. I think that's a great question. It's probably out of scope. 5 tuples, great metadata to use though. DNS servers are another fun place to mine for potential data. Like I see things going to ntp.netgear.com. Hey, maybe that's a sign.
Yeah, and that was the way they addressed this, so that it wasn't hardwired.
And I forgot what the other one was.
Thanks, Lee. I think we'll
Matt Mathis, it strikes me that the best signals from this kind of experiments are the ones that were accidental, that any signal that you design turns into a security problem. But for instance, that the port numbers were unique or unusual was an accident, and that in itself turned into a very valuable signal. And I think that's actually going to be a pattern that's repeated, that the best signals come from detecting signal that were never intended.
All right, thanks.
Yes,
Ben.
fingerprinting.
So intentional accidents, we should have. Okay, thanks. So Giovanni is up next.
Yeah, thank you. So yeah, I'm going to talk about any CAS and DDoS, about the root DNS events that happened in November 2015. This is joint work of SIDN Labs that I work for, that are now Registry, USC, and University of Twente in Holland too. I think I have 2 of my co-authors here. John is in the back there, and Ricardo must be somewhere here too, I guess. There we go. So it's pretty simple, IP and CAS. I'm not sure how many of you guys are familiar with that. I assume almost everyone here it is. But it's pretty simple. There are 2 RFCs that define it. And it just makes a service which is to be available in multiple discrete autonomous locations. And basically, you don't have the map in between an IP address and one machine. You can actually have many hundreds if you want, spread all over the world. So the idea is that it would provide increased performance and resilience. It's widely used also in DNS and also CDNs. And on the other hand, we have DDoS. It has a totally different goal, which it aims to bring down those things and anything that it attacks. And the problem with the DDoS, it's getting cheaper, it's getting bigger, it's getting more frequent. And we wanted to know how actually the Anycast infrastructure handles a DDoS attack. And we use as a case study the root DNS events of November 2015. So if I'm sure if you guys follow that, but there was an attack on the root DNS system, and we did this draft. There's actually a technical report. There's also a paper under review now. You can also download and check it out. So quick catch up on the root DNS system. It's actually 13 letters. That's all they call. From A to M, they're managed by different operators here, 12, all of them. And 11 of them are actually Anycast. And this is the number of sites they have. And only B, at the time of our research, was a single site. And H was like primary and backup. And so when you try to resolve a domain like that, you just ask the root DNS service where is .com or .net or .whatever. You don't ask like for the fully qualified domain. And actually your resolver mostly does that. So when you ask them, usually you end up one of those 13 letters, and the site you're going to end up, which city, is decided by the BGP. So a bad day in the root. So this is DNS1. It's provided by RIPE. They have the probes. And everything in green here looks fine. Everything in red looks bad. And pretty much there was a lot of packet loss, above 30% here for each single letter. These are the letters IPv4 and v6. And most of them had problems. And we wanted to investigate what happened and what does red mean, and red means, and also what does Anycast versus DDoS means. And the events, you can summarize them. It attacked like I think 10 of those letters. They were actually 2 events. One happened on the 30th this time, lasts for 24 hours and 40 minutes. And the other one happened the day after in the morning. Affected 10 letters out of the 13, 5 million queries per second. And per letter that were attacked. They were real DNS queries, they were spoofed. And the implications based on the reports of the root servers and also VeriSign's presentation of the last DNS work. That some letters have problems, have very high loss. But overall, the DNS worked fine because there's a lot of redundancy built in. There's a caching, so it also helps. And for the clients at home, mostly what they suffer was just a little delay, if most. So how well Anycast defended? This is the root DNS system where the sites are located. There are 561 root DNS sites around the time for the 13 services. And we wonder if that's too many to fill And in the good times, what any cast does, and let's consider here a random letter of any cast, which is X. If you're any cast, you have a single IP address, and let's say that X letter has 3 different sites. So the same IP is hosted in San Jose, in Prague, and Sydney. And on a good day, if you're sitting here in San Jose or LA, you will send a query to the San Jose, you should actually go to San Jose. BGP should bring you to the closest node. Same as your friend in Prague, same as your friend in Sydney. So what Anycast does is that pretty much everyone in this area would go to San Jose if they query for X. And these guys here go to Prague and other ones to Sydney. But under attack, things might be a little different. So assume that the attackers are actually targeting the IP address of X, and most of them are redirected to San Jose, and this site is overwhelmed. So your queries are going to be lost. You're not happy. You're red here. But on the other side of the same IP address, the sites might be a little too big to handle the attack that they receive, so they'd be fine. And your friend in Sydney might not even be attacked. And what can you do about it? There are things you can do. You can just do nothing and then watch and see what happens. And if you don't do anything, pretty much San Jose can act like the greater absorber, because it's going to be like beholding these attackers in here and making sure that they stay here. You're going to have a problem. One person is not going to be happy, but your friends are going to be fine because your friends have a bigger site and the other one is not even attacked. If you withdraw some routes from San Jose, from the site, and the attackers are then deflected to Prague, which is a bigger site and can handle that, everyone's going to be happy. This is just a toy example, of course. And if you withdraw the wrong routes, and you go up to Sydney, and Sydney gets overwhelmed, 2 people are unhappy, and only the guys in Prague are happy. So the message is, best reaction to stress, you just don't know it. You don't know the number of attacks, the location, how effects of routing changes. You don't fully control routers and catchment, and it's hard to make informed decisions. Okay, so what actually happens on that day, November 30th? We saw both things. We saw withdrawals of routes. We saw degraded observers. And some clients lost their service, and the results vary significantly per Anycast service. To analyze that, of course, we use public data, right? Atlas, I think everyone here is familiar, don't need to go over that, but basically 9,000 vantage points from all over the world. They probe each single root letter every 4 minutes, with exception of A. They were 30 minutes, but then they fix it. Thanks a lot for that, by the way, RIPE for providing that for us. It's all public. Also, our Cycle2 reports and BGP monitoring. And so what happened to each individual letter? So in this figure here, we see the time series for all the figures. They're all the same time. And this dash line here indicates for every figure when the talk started. And the number here, in this figure, for example, for K, around 9,000, means the median number of probes that reach each letter before the attack, when the operation was normal. And you can see they're all stable, around 9,000. That's the number of vantage points. However, during the attack, it's really synchronized the number of probes that can actually reach them. What is happening here? So for example, for B here, most of the probes, they could not reach B anymore. And even though they try every 4 minutes during the attack, and then eventually the attack stopped, and you go back again. So different letters have different responses here during the attack. They become unreachable. And the ones that D, L, and M were not attacked, the A, we couldn't see anything because of the frequency of the measurements back then. There's a great VeriSign report on that as well, DNS work, as I mentioned. And the one that suffered a lot was B, C, G, and H. But of course, you still wonder, what is this X% of the loss really means? And as I said, when you have a letter, like X or K in this case, you can be deployed, you can have it deployed over 44, I think K was 32 sites, if I'm not mistaken, around that time. So 32 cities, and you can see like K, Amsterdam, London, we just normalize the names, Frankfurt, whatever. This is, in parentheses here, show the number of probes, of write probes that would reach them on a median number every minute measurement. So this is the natural catchment before the attack. And when this talk started, you see there's a drop in the number of probes for London Heathrow here, and the median number is this one here. And then once the attack stopped, it started to go back again, and there's a little spike here. We see London taking some probes extra, and then it goes down again here. So some sites have different responses you can compare here. This is all synchronized with the attacks. Amsterdam basically, just went up, it seems. London went down a little here. So why does that? Why do we see this difference in here? You have to think of a letter as a single IP address, and like a mattress, they're going to absorb the attack over different parts of the mattress. Like kind of like waterbed mattress will take the load in different parts. And we call this term the side flip. And a side flip means that imagine you have a probe imagine you live in Amsterdam and you have a probe located in Amsterdam. You're going to go to the K-root instance of Amsterdam all the time. That's because, thanks. You're going to go for the instance of Amsterdam because it's closer to you, and or if you live in London, for example. And in this figure here, we take like, I think, 40 probes, and you show the measurements that happen every 4 minutes for them here. And what happens here, the yellow color here show the probes that are reaching London, K-London instance, and they are all reaching London, everything is fine here. And once queries start to fail, it was when the attack started here for November 30th. These guys here, these probes on top here, they would become like, let's say, sad during the event because they will lose all their queries, most of the queries during the attack. And once the attack was over, they would remain there in London and they would get responses again. Now, another set of probes, they would actually, what we call flip to Amsterdam. So when they are trying to query K, which is the same IP address, something in the network would change like a BGP route, and they're going to start to show up like being responded by query by Amsterdam. And they remain in Amsterdam after the end of the attack, and then they go back to London. Some, they flip from London, which is this color here, to another K site in other cities. And some probes, they flip to Amsterdam. They were yellow London, blue Amsterdam, and they stay in Amsterdam. So you can also confirm these flips if you look. This is the time series we've seen during the attack, looking at which sites they're reaching. It did this per letter, and there are spikes when the attack is started. And you can see also these flips happen in the BGP tables announcements. If you look at the BGP mon here, you see that it correlates these two things here. And we also have this figure here that we look at the entire E-route here. I think E-route is run by NASA and K-route run by RIPE. And each individual point here shows a different site. And so I think it's very small here, but you can pull it up in the paper. But what I want to show you here is what happens during the attack. This number 1 here means the median numbers of probes that they get on average. And some sites, they get like more probes at a certain point. That's the maximum value, which means they are taking over the load of other sites, and other sites just go down here. So there's a shift of the balance of the number of probes during the attacks, and you see the same thing here. So some sites acquire vantage points, some others they shed there during the attack. And what are the implications? So some ISPs are just sticky; they won't flip, so they use the suffer modes in there. Some ISPs will flip, but they might flip to a site which is not much better. And results depend on manufacturers, the actual stakes by the operator, with the peers, and maybe the peers, and DNS and routing, a lot of stuff. And we also found interesting collateral damage. If you see like the D-route was not even attacked, there's also drops in the number of queries that they see because there's less traffic. And also for .NL, this is only private data we use on this report. This is our own instances for .NL. And you see that during the attacks as well, .NL had, for Frankfurt and Amsterdam, they had no queries. And why is this happening? Because of co-location. If your data center in which you host your services is attacked, one of the servers that they host is attacked, it might go down as well. There's a great report by Proton Mail that happened to them, and they were hosting a certain data center, all the other services went down. So conclusions, NCAS under stress is very complicated. Some users receive persistence loss, and just a percentage is not a complete picture. And of course, reactions depend on design and implementation choices and might not even be under control of the operator. So if you have questions and the data and the paper, you can find them here. And I'll be happy to take any questions.
Thanks, Giovanni. We have time for one question. Maria, do you want to use? I'll ask then. No, we're saying from the way MAPRG is formed, how is this instructive for the design or operation? So do you have anything that's like a recommendation about, you asked a couple times rhetorically during the talk, is this enough locations?
Yeah, so we just show for our case study what are the policies you can have. You can withdraw routes, you cannot withdraw routes, you can keep them. And what we show there is it's much more complex. It depends a lot on the attack you're going to have. So it's way more complex, and people should be prepared for that. It's hard to make informed choices. Yeah.
All right. Thanks, Giovanni.
Quick question. Do you know if any, Matt Mathis again, do you know if any of the withdrawn routes were deliberate, or were they also collateral damage?
That's a very good question. Some routes might be dropped by expiring BGP sessions. We didn't have access to this information. Thank you.
Yeah.
Oh,
Quick.
sorry, one last, quick question real quick. I'm getting there. KCDCO. So a lot of your measurements were looking at single vantage point and then single site. Were you able also to look at those? So I mean, and that's great data. I think it was actually this is a really useful study that you did. So thanks for that. Were you able to look then also at single vantage point and multiple sites to kind of see what the dynamic was as one site was changing? What was another site doing over time?
Yeah. What we did, like, because the RIPE Atlas probes, no matter how,
sorry, let me correct my question. I mean, not sites of a single instance, but different instances, like different letters at the same time.
How the same probes would behave in regards to different letters?
I mean, so you have a single probe that has, you know,
we have 9,000 probes.
Sorry, single vantage point. And now, what does that vantage point look like as these changes are happening across multiple sites, but they still have the 13 different instances of root servers to look at?
Yes.
That are like themselves across different sites. Does that make sense?
Yeah. So each probe, they have like different. So the way RIPE did, they have one measurement per root server letter, right?
Correct.
And so per time, you have a measurement from each probe to all the 13 letters. We didn't do the analysis looking at individual probes and how many of the letters they could reach at a time. That's something that can be easily done.
Okay.
If that answers it.
Yeah, that's fine. We can talk more offline. I just, it wasn't as quick a question as I thought.
All right.
Thanks.
Thanks, guys. And Varun is up now.
Thank you. Thank you, Jess, for inviting me. So I'm Varun Singh. We run a startup called Stats.io. We started operations about 2.5 years ago, and we've been collecting data over the last 2 years. We have about 200 companies using Stats.io in various deployments of WebRTC. So how it works is our customers take our JavaScript and put it in their web application. And when they deploy the application to their end users, the end users automatically, when they make a call, start to send data to us. Typically, the data that we get is from the start of the call till the end of the call. We collect various things, including network statistics. And so we collect network statistics, we collect media statistics from the pipeline. We get all the audio, video, dejitter, buffer information. So everything that once the packet's generated and sent out, and on the other side when it's received and played back. We capture all these metrics. In some cases, we aggregate these metrics into something that we call annoyances, mainly to abstract ourselves away from like specific metrics like RTT loss. We aggregate it to see if the user experience perceived by the end user might be good or bad. We typically show things to our customers on a dashboard. One of the most important metrics we show is disruptions, where we say that the quality of the call for this duration was either really bad because either the losses were quite many, or the RTT was very high, or the throughput was very low for things to be played back accurately. What we also do is we get feedback from our end users, and additionally, we also capture what they do on the website. For example, if they press the pause button or they stop sending video or restart the call. So one of the things that we see is disruptions and user behavior. So typically when they're not able to see or hear something, we see the end users try to diagnose this problem by themselves by either turning off their audio and video and turning them back on over a small period. And in this graph, as you see, there are like 3 people in a call, which are simultaneously experiencing disruption. And what they're trying to do is they're trying to debug the call by themselves by like turning off audio first, then turning off video, and then turning that back on to see if they're getting any audio video back across the network. So that was just a quick intro as to what Stats.io does and how we measure data. We have a bunch of metrics that we've collected over the last year. This is what we call the state of WebRTC as we see it. So that's a caveat, as in it depends on what kind of data and what kind of deployments we have. Doesn't say anything as to what the state of WebRTC is in the wild. So one of the things that we measure is like how many multi-party calls are there on the internet today. So what we see is about 60% of the calls are between 2 parties, and the rest are for more than 3 persons. about 11% of the logs that we see are for legacy interconnect, where we only get data from one party and not from the mobile phone or fixed line phone. So 45%, 40 and 44% people in a call are more than 3. So we start to see emergence of calls where there are more people in a call on average. So we also measure networks. So we said, okay, since this is WebRTC and people do ICE, we want to know like if there's IPv4 and IPv6. What we did see is about 76% or 72% of the calls had only IPv4 addresses. About 2% had only IPv6 addresses, and the rest had a fair amount of IPv4 and IPv6 addresses. This is quite heartening because about a year ago when we did the same study, we saw only 3% of the calls had v4 and v6. It's also to say that our deployments have also increased, like the number of things that we are monitoring has also increased. So there's both the fact that we are monitoring more and the fact that the numbers of v4, v6 is increased indicates that we start to see more traffic with v6. Another thing that when WebRTC works, there's a bunch of ICE candidates that are collected so that the two endpoints can exchange them and do like happy eyeballs, like check each other's pairs, right? So one analysis we try to do is how many candidates do we typically have on an endpoint? And what we see is that majority of the cases we have about 4 to 8 candidates, but in some cases we also see something like 24 or 25 candidates. So that means the checklists are really long, and like if both parties have 24, then you actually have to do a check over the whole list. So some of the things that we try to figure out is why do we have actually so many? So we have v4, v6, and you also have like host and stun candidates and sometimes relay candidates. So typically for each class you have 3, and if you have v4, v6, then you have like 6. And if you're multi-homed, you'll have even more. So so there is a reason to see more ICE candidates gathered. Another thing we notice is that 24% of the calls need infrastructure. So when you try to establish a connection between two parties, sometimes because of NATs and firewalls, they're not able to go through. So in 24% of the cases, you need some kind of relay server through which would establish the call between the end users. What we also see in the fact is the fact that in the 24%, about 8% of the calls cannot go over UDP. And need to go over TCP because of either corporate firewalls or really very restrictive firewalls where UDP does not go through. So we see about 8% of the calls either go through TCP or over TLS. So this is also a fair question because then you have two congestion controls. You have the RDP congestion control and you have the TCP congestion control. So something for people to like take note of. A few months ago, at another place, we noted that there were 12% call failure establishment. That means when people try to connect with each other and to exchange their IP addresses, in 12% of the cases, due to various other factors, including ICE connectivity, the call was not established. But over the last 4 months, we've tracked that the 12% number is actually reduced to 4%. This is largely because some of our customers were not using relay servers, which was leading to a higher rate of call failure, and with this addition in infrastructure, they were able to like route or establish calls for those customers that were behind firewalls. In the same period, we also saw our traffic double, so it's not a fair comparison in the sense that it's 12% 4 months ago, and in 4 months we've doubled the traffic, and actually 3 times the failure rates reduced by 3 times. So when we say something failed, there are various reasons that may happen. So one may be that when you go to a website and suddenly asks you for a question like, give me access to your web camera or mic, people may say, oh, I don't want to give you access. Sometimes that's one aspect of it that's permission related, but there might be other things like the camera might not be configured correctly, or there might be bad configuration. Then there's some connectivity issues, which are 85% of the reasons where call failures occur. And about less than 1% of the failures occur due to negotiation. So where a browser or an endpoint is unable to negotiate the right parameters or configuration for the call to be set up. We also note that once the call's been set up, in 12% of the cases, the calls drop. And for more of that information, about 80% of the call drops are due to connectivity. So either because there's loss in connectivity, which either cannot be, we try to distinguish it. In some cases, we replay the last 5 minutes of the call or the statistics and try to identify if there was an increase in loss or increase in RTT. In about 12 and 17% of the cases, we were able to identify this to be persistent 100% packet loss in the last 10, 20 seconds before the call failed, or in some cases, very high delay, which means like about 4 or 5 seconds of delay on the last 10, 20 seconds before the end of the call, which would result in the call to be dropped. And in some cases, we see that there are pipeline issues where the call is set up and you can see a person, but unfortunately not able to hear the person, which we call one-way delay. And this sometimes happens because either the media stack is unable to connect or is unable to connect the audio or the video into the pipeline, into the network. Therefore, you either just hear one person, you can't communicate with each other. Another thing that we notice is round trip time. Since we've been collecting this for a while, we took all the calls over the last year, took 95% of the RTT for each participant in a call, and we binned it in 50 milliseconds, 50 to 150 milliseconds. What we do note is the fact that about 80% of the calls are under 400 milliseconds of RTT, which is really good given the fact that it's interactive communication. Although we do see in 4% of the cases that the RTTs are over 1 second in some cases, and there's 95 percentile. So in these cases, they were a significant number of calls which had 95 percentile of 1 second RTTs, or more than 1 second RTTs. So in summary, what we see is that there's still participants are in a call are still 2 participants. The relays needed for a call are 25% of your infrastructure needs to handle 25% of the traffic. Setup times for most of the calls are less than 5 seconds. About 4% of the calls fail to set up. This is reduced from 8% a few months ago and 12% earlier this year. The major reason for call failure is NAT and firewall traversal, which is 85%, and about 12% of the calls fail after setup. And the major reason for that is connectivity issues. Again, so thank you for your time. This was just a summary of results that we've seen over the last few years.
Thanks, Varun. We have about 2 minutes left for questions. I have an initial question. Early on, you showed 2% of them are V6 only. Where in the world is there a browser that thinks it has V6 only?
I think it's mostly Europe. Like when we looked up, yeah, I actually haven't really looked up why there's only V6 only. Probably should plug.
It's pretty high. It'd be interesting to know.
DHCP was timing out.
I'm sorry?
DHCP was timing out.
Yeah, something like it's not. You're
killing 2 birds with 1 stone, right?
Sometimes it happens.
Yeah.
2% of timing.
I believe you guys. It's an interesting phenomenon.
Anyway, I don't know any IPv6 only network in Europe, but I can be wrong. Eric Ving from Cisco. Again, on IPv6 topic. Do you have the data that shows how many IPv6 enabled nodes are relying on turn server?
Yeah, we do have that information, but we've actually not plotted.
Is it higher, lower? Because normally there is no NAT, but there are firewall blocking inbound connection.
I think in some cases it might be that some people's happy eyeballs V6 connects to V4. I've not really diagnosed the turn V6 really much, but that might also be the fact that some infrastructures really don't have V6. Like for example, AVS does not give V6 addresses very easily. So if you run a turn server on Amazon, I'm actually not sure, but I think they don't give V6 addresses. So we've not really looked at turn over V6, but this is something that we can look into and get back to you.
Yeah, would be nice. And the last one, of course, is about the RTT. Do you see a difference between V4 and V6 there?
We actually we didn't look at it. We just like did an aggregate, and both good questions. I think we'll look at it in more detail.
I'm really interested. Thank you.
Can we cut off the line? We really don't have any more time.
Lorenzo Cludi, like actually it's a duplicate of the previous question, but also do you have data about firewall traversal in IPv6? Is it better? Is it worse?
I think we have all the data. That's not a problem. I think we just haven't had
present the data.
Yeah, we've not even had the time to actually look at the data in much detail. But I think this is good input that we should look at V6 both from a network dimension and throughput and things like that.
Michael Turkson, do we also have data regarding data channels or only audio video channels?
We do have some data channel data. It's separate because it's mostly from companies which do audio video like BitTorrent kind of traffic, not from companies that actually use audio video only. But I'm happy to share it with you.
Okay, that will be interesting.
Cool.
Thanks a lot, Barry. Okay, we're going to switch. Johan is up.
Hello, my name is Johannes Klick, and I want to talk about temporal and efficient analysis of service availability. So if you want to measure deployment of internet services in the past, most researchers are scanning the complete address space, or only the LAIANA allocated, or only the BGP announced prefixes, and or they use the IP hit lists. But is this a really good idea? Yeah, maybe not. So we have several problems with this easy kind of scanning all. So at first, mostly the hit rates are under 2%. This means that from 100 TCP SYN packets, only 2 getting full responses. And furthermore, we have a lot of abuse reports. We have rate limiting on routers. We have intrusion detection systems that also can have impact on our results from our scanning approaches. And in the end, we have also IP blacklisting as a result. So in the end, we could say, yes, maybe we should scan less, but how is it possible? So we want to propose a solution called TAS, Topology Aware Scanning Strategy. Our idea is to perform a full IPv4 scan once, then to select prefixes with a certain coverage of responsive hosts. For example, all prefixes with at least one host responding. And then we can scan only these prefixes for a given time period. So we have analyzed this kind of technique and have found out that it's possible to reduce the scan traffic from 25 to 90% by missing only 1 to 10% of the results. So how we are doing this? At first, we need to get the prefixes. Therefore, we are using the KIDA database, root views prefix to S database. But the problem is that the prefixes in this database are not complementary. So this means we have less specific prefixes containing more specific prefixes, like the /8 prefix containing several /12 prefixes. This is a problem for us because if you want to look up a prefix for IP, we will get more prefixes than one. So therefore, we are doing the following. If we have a /8 prefix in a KIDA-S database and also in containing /12 prefix, we are decomposing the /8 prefix into several sub-prefixes so that all prefixes are complementary to each other. Okay, so in the following, we have analyzed our method for taking only the less prefixes called L prefixes or our resulting M prefixes. Okay, at first we have here a necessary condition that we say, yes, we have here our for FTP and HTTP, we did the analysis. We have here the number of hosts per prefix length and see that FTP hosts are very often in /18, /19, and /20, just taking only the less specific prefixes. And we see that the box plots are really small. This means we have really, really stable results. This is also kind of similar for HTTPS. We also can see that the distribution per prefix length is protocol unique. So HTTP is more in smaller prefixes than FTP. And furthermore, that's a more important point for us. We see when we use the decomposed smaller M prefixes, we have also stable results for our prefix length. This means that we can use, as a necessary condition, we can use these prefixes. So now let me explain the more interesting part. We are taking all the prefixes with at least one host and sorting them by their density or utilization. Density means if we have a prefix with 100 possible IPs and we have 50 responsive hosts, we have a density of 0.5, right, 50%. So we are sorting all prefixes by their density. You're seeing, where is it? Here, from high to low. And then we say, then we look for what is the host coverage. This is the cumulative host coverage. And here we see the cumulative address coverage. So just give me some example. If we scan if you want to have all hosts, this means a host coverage of 100%, we can scan all prefixes with at least one host, and this means we need only to scan 80% of the advertised IP address space. If we just say we want to have 99% of all HTTPS hosts, we need only, 99% is here, we need only to scan about 55%. So this means we have half the effort of the standard TCP SYN packets. Or if we want to say we want to have 95% of all HTTPS hosts, we need only to scan about 35%. This means now it's a third. So this is for taking only the less specific prefixes. If we want to take the more specific prefixes, we see that we are in this area 20% better. This makes also more sense because the prefixes are smaller, and so you're picking only the right prefixes, you're not having the huge prefixes. And furthermore, you can also say you want only every second host. So this means a host coverage of 50%, then you need only to scan under 10% of the whole IPv4 advertised address space. So, but now it's important to say, okay, yes, interesting, you have your prefixes, you're scanning them, but how stable are your prefixes, right? So at first we want to compare with IPv4 hit list with the data from Census.io. We have analyzed 4.1 terabyte. Here we can see that if you use hit lists for FTP, HTTP, or HTTPS, you have after 1 month only 80% hit rate, and then later after 6 months about 75. If you're using CVMPs, it's a protocol for management of small office, home office gateways, also called TR069. It's typically used by a lot of devices that are connected via dynamic IP addresses. You see that the hit rate drops really fast after 1 month, after to 60%, and later to 50%. So this means hit rates are not good, usable for scanning once and scanning again and scanning again, because you are losing a lot of results. You get a really bad host coverage. Okay, so now analyzing of our method test, we see that if you're using our prefixes by initial host coverage of 100%, we see that after 6 months, we are about 99% host coverage. So this means if you're scanning once and then scanning again and again all prefixes with at least one host, we are missing after 6 months only approximately about 1 to 2% for our less specific prefixes. And if we are taking our more specific prefixes, we are missing about 2 to 3%. So, and if we are doing this with an initial host coverage of 95%, which, keeping back in mind, means that we need only to scan like 35% of the advertised IPv4 address space, we are only missing for our less specific prefixes 1 to 2% from the initial state, and for our more specific prefixes, we are missing like 4 to 5%. So our future work. So that's our first idea, so our first evaluation. What needs to be done in the future work? So interesting is what is about the distribution of the skipped hosts? So what are they host unique or typically on high dynamic IP addresses? So this has to be done in the future. Then we need to a better understanding of the autonomous systems types. So are there some autonomous systems that are very often skipped by our method or not? And we want to analyze more protocols and the longer time periods. And final, very interesting question is how is this method applicable for IPv6 scans? Okay, so thank you very much. If you want more details, you can read the paper. It's already under submission. Questions?
Thanks, Johan. We have a couple minutes for questions if there is something. When we were discussing whether the topic matched the working group, the one that was most interesting to me was the rate limiting that happens in routers. Especially we're confronted with that in v6, but it's also there in v4. Can you speak anything to that about that? Is that really the compelling reason why you pursued the technique, or?
Sorry, I didn't get the last.
The part is that a compelling reason to use this technique to not use up all the tokens basically in routers so that you can't do the active measurements anymore? And what's the value of doing this instead of just doing the full scans?
What is the value of doing this this technique for IPv4 or IPv6?
By trying to whittle down the number of probes you do.
Well, the value is that we are able to get quite similar results by scanning less, because I have shown before that if you're issuing a lot of SYN packets, this can have impact on your results. At first, one point is the ethical point, right? So we are doing a lot of research, and this has impact. So we are getting abuse messages. Also, census reported that there are some law points. The lawyer had written the census team to decrease their scan pressures, and also intrusion detection systems and routers. So especially for IPv6, the RFC stands for IPv6 ISMP, that after some high rates, there will be drop-offs, and this can also have impact on your results. So therefore, we need to scan less from an ethical point and also from a point for our data quality.
All right, thanks, Johan. Tommy, you are here? Tommy Pauly? Oh, yeah, there you are.
Hello, Tommy Pauly from Apple, and we'll be sharing our view through happy eyeballs. Essentially, we've just started collecting some data around how much we use v4 versus v6 in our libraries. And we have a lot of large-scale data that we've seen from the provider side, the CDNs, but we'd like to give more information of what the client sees, because we know when we're essentially racing multiple connections, and that can give a kind of different view on the data. Yes.
You can if it doesn't work, I just changed it myself.
Okay, thank you.
Just ask me if you don't.
All right. So for background, what do we do? So on iOS and macOS, we use this algorithm for creating a list of addresses and then trying them in order. So we first sort our addresses. We use RFC 6724, and we also sort them based on some happy eyeballs style logic. Essentially, we just want to make sure that there are some v4 and v6 addresses at the top of our list. If we have v4 first, we'll do v6 next. If we do v6 first, we'll actually do potentially 2 v6 and then 1 v4. We're a little bit biased towards v6 because v6 is good, but in general, we're trying to be fair here. And then we'll go through and actually try to connect to those addresses in order, and we have a timeout based on the RTT invariance to move on once a particular connection has not become fully connected yet. All right, next slide. So what are we measuring? So we've started randomly sampling 1% of all connections that go through our library, and this is used for most of your apps and browsing on iOS and Mac. And we started measuring this just for the public beta of iOS 10 and macOS Sierra. So all of this data is coming from just about the last week, so very fresh data. We're collecting a lot of things, but the relevant things for Happy Eyeballs and for V6 are the number of addresses that we received back from DNS, V4 and V6. What was the first address family that we attempted? Generally, this will be V6, but if we know that historically V6 has been slower than V4, we'll potentially rank V4 higher. Which address family ended up connecting? The connected address index, which means how many addresses did we have to try before one worked. So if it's 3, the third address we tried connecting to actually ended up connecting before the first 2. The TCP handshake time as well as the interface type. Next slide. Okay, so how often do we actually connect over V6? So this is just kind of the overall breakdown of what we're even trying. So as somewhat expected, a lot of the connections we try to make are using DNS to things that only resolve to V4, either because the network only responds to V4 or the host name, the server itself only has a V4 address. We see there is some percentage of V4 literals being passed to us, so that's not good. We're around 5%, very few V6 only. But the interesting part is that we're around 6% of V4 and V6 host names. So let's dive into that. So overall, for everything, we see 94% going over V4, which is not surprising considering the last number you saw. But when we just look at the V4 and V6 host names, we see that 87% of the connections end up actually establishing over V6. So this is really good for V6. So that's kind of the overall numbers. When we break it down by interface type, we see that Wi-Fi is around 85%. Cell is a little bit better generally, around 90%. And interestingly, in our measurements, people who are using wired Ethernet had a lot less V6. I'm assuming that this is because people who are still plugging in their Macs to Ethernet cables are on enterprise environments or have some networks that are treating V6 differently. But in general, we see pretty good stories for Wi-Fi and cell. Okay, so how often do we actually need to use our racing algorithm? When is it actually relevant to try multiple addresses? All right, so this is a little bit complicated graph, but I'll try to explain it. So essentially what we can see here is that when IPv6 actually wins the race, when we get connected over V6, it is 99% of the time because that was the first address we tried. We rarely fall back and end up actually working over V6. When we end up connecting over V4, about 2/3 of the time, it's because we knew V6 was bad on that network, and we ended up trying V4 first. And 1/3 of the time, we actually tried V6 first, and something went wrong, and we ended up falling back happy eyeballs to V4. And these are percentages of the time that we end up connecting over V4. So if we go to the next slide, another view of this is that when we try V4 first, we very, very rarely fall back to V6. But when we try V6 first, about 5% of the time we have to fall back to V4 for some reason. Now I think this is because we do, as I mentioned, have a little bit of a bias in favor of V6. And so it looks like our bias costs us about 5% of the time being wrong, but this is still pretty good for V6. So we don't see any more than 5% of cases in which V6 seems to be broken. All right. We also collected some latency measurements. So overall, the handshake latency for V4 and V6 is about the same. They track each other pretty well. So we're essentially bucketizing how long the connections took for both V4 and V6. And you see they mainly cluster around the 20, 40 millisecond range. And V6 does trend a little bit faster, a little bit better than V4 for everything above that. So then when we break it down by interface, we see that that exact tracking actually gets a lot more interesting when you look further. So when we're on Wi-Fi, we see a similar shape, but V6 is noticeably more clustered towards the fast connection. So we see V6 seems to be faster on Wi-Fi pretty reliably, so that's good. Cellular has a much more interesting graph here. We see kind of two clusters in which V4 seems to cluster faster than V6. V6 clusters about 20 milliseconds slower than V4, but in higher volume. So V6 is more consistent, but it seems to be slightly slower overall. We were looking at this with people today, so I actually broke apart the numbers a little bit more. So I split it up by carrier. So there's a subset of carriers that we know are promoting V6. We know that, we noticed from the numbers that V6 connections on their networks worked much better. And so when we just look at those carriers, we see a very different story, much faster on V6 than V4. And then we look at the rest of the data, we do see that, as we'd expect, V4 is faster than V6 on these other networks. But it's also interesting to see that they are also generally, for some reason, faster than those V6 friendlier carriers. So interesting data. And then on wired Ethernet, everything's really fast and V6 is super fast. So that's good to know. Ethernet still works. And that's all the data we have. So any questions or insights?
Lorenzo Coliti, I wonder if you could use stuff, if you could use something to detect these like men in the middle that you have.
Mm-hmm.
Like the SYN-ACK latency is going to be entirely a function of whatever man in the middle you're talking to.
Yep.
I wonder if there's something else you can do, like looking at ACK clocking deeper into the TCP connection or something.
Mm-hmm.
Is there something that you can do there? Like on keep alive connections, for example, when you if you measure the time to first, like the time between request and response of some static thing that you've already requested. I don't know.
Mm-hmm, mm-hmm. Yeah, we aren't gathering that right now. That is definitely, we want to look further into the connections for upcoming data, but
would you find what I know? Would you actually find what you're looking for, though? I wonder. I mean, have you thought about this? Do you have something that you think will work?
Not yet, but we'd love to get suggestions and chat about.
Because it is a crying shame when networks that have V4 transparent proxies
mm-hmm.
and like experimental data saying that V6 is faster on those networks are racing to deploy V6 transparent proxies as well. That just seems silly. And so if we had data that could counteract that.
Yeah, that's a good point.
So time-wise, if we stay 5 minutes longer, then Runa has all her time. If we take these questions and don't stay 5 minutes longer, she doesn't. So if you're willing to stay for 5 minutes, we can take these questions and we'll end at 8:05 p.m. Is that okay?
Okay, so Olivier Valentin, I have two questions. The first one, I have the impression from the slides that you take all the connections that are initiated by the device,
mm-hmm.
and then you sample them at 1%, whatever the destination,
mm-hmm.
and you send the information back to Apple for analysis. Is it right?
Yes, we essentially, when our library initiates a connection, we flip a coin and choose 1% of those as eligible for tracking.
Okay, so as a researcher, I think this is a really nice data set. As a user, I'm not sure that from a privacy viewpoint, I'm happy to see this kind of information to be sent directly to servers for any destinations that I reach.
Sure, so we don't have any information whatsoever about IP addresses, host names you're connecting to. We just know, V4, V6 breakdown. And these are only for devices that have opted in to data collection.
Yeah, but you have information about the carrier, for example.
These are only for people who have opted into data collection.
Okay.
So.
Last question.
Thank you for the report. I wonder, do we have some historical data? Because I think it would be very interesting to see if this gap in latencies between IPv4 and IPv6 is changing or not.
I agree, it'd be very interesting. We just added this. The first data set we have possibly had was from last Friday. And so I would love to report back in a year and say how it's gone.
Okay, thank you.
Runa's up next, and I'll have to change the slides for you because it seems to be dead. So just let me know when you want to change.
Hi, I'm Runa from University of Oslo, and this work is related to DSCP and EvilBit. Okay, next. Okay, so this discusses that when the users are interested to get some special service by the network, it is better to use the IP header. So that is our main focus, to see how the internet behaves with the IPv4 bits, header bits. Okay, this is also another thing is that the middle boxes in private networks, mostly the home networks, they also modify the packets. So we are interested to see how they behave with respect to this IPv4 header. Then this complements the paper that is recently published in NRW 16. Okay, so we want to know how the middle boxes behave with these bits. Okay, next. Okay, this is our test methodology. What we do in this, the client will initiate the connection, and here we send a test packet, setting some DSCP value, and the server will respond with another packet. So the client can be from any number of places. We have servers in 3 places, in Norway 2 server and 1 in Amazon cloud. Then, okay, so the idea here is we send a TCP SYN. Okay, so the test is related to DSCP. So we are sending TCP SYN and the SYNAC response by the server. So what we use, the tricky idea is that we send a ICMP packet with the TCP SYN packet and SYNAC packet. So what it does is that the use of this ICMP packet has 2 folds. Is like if the ICMP, we assume that ICMP will pass through the network. So if the TCP SYN packets with a specific value, DSCP value drops, but ICMP just suppose a 0 DSCP value and it passes, then we can understand that if the ICMP packet passes, then we can say that this is a drop by the middle box. The same goes to SYNAC packet. And we repeat the test 3 times to see is that the drop is consistent or not. Okay, next slide. Okay, see here, we want to detect in which direction the particular DSCP value, packet with DSCP value drops. So what we do, here, the TCP SYN and ICMP packet share the same identification field in IPv4. If the packet drops and the ICMP packet reaches the server, so then the server will respond with the same ID in ICMP reply packet. What it does, when the client will receive that, then it can understand the direction of a packet drop. And the same thing goes to the server side. If the server packet is dropped, the client will receive a ICMP reply, then it will send back with ICMP request another, such that when the server will notify it, get it, then it can say that, okay, the server packet is dropped. In this way, using this ICMP as an anchoring message, we can understand the direction of a particular packet drop. And after detecting there is a packet drop, we use a trace route or trace box like a test, and where the packet is actually the test packet. Either it is TCP SYN or SYNAC with increasing the TTL. Okay, next slide. Okay, this test, this was the test when I traveled from Norway to India, and I was attending a conference in Malaysia, so I was trying to do the test from different places. So one IP, I did not travel to UK, but one IP belongs to UK, because when I was traveling, the IP in a flight, I was doing the test, and the IP I checked, it was belonging to the UK. Okay, next slide. Here, I am presenting that the DSCP values with respect, and see the statistics. Okay, how we choose these DSCP values? Basically, we follow, we refer to the one draft, that is RTC Wave QoS. In that draft, it mentions a table that how to use the DSCP value with respect to some type of traffic. So this, we choose the traffic like interactive video with and without audio. So 0 has low probability, and 8, this 8, DSCP value 8, basically it is 32 as integer, we divide by 2, so it gives 8. So 8 represents very low. And if you go next slide, thank you. Here it is 36, which has medium priority, but 46 represents the audio with high priority. If you'll go back, yes. So here we see that here the big number represents what value we sent in the TCP SYN or SYNAC, and the smaller number represents what value is received by the server or receiver or the client. So we can see that 0, okay, the above tuple represents 0:185. For example, 0 is the number received and 185 is the number of paths where here we consider paths as a IP address pair. So 0 remains 0, quite high probability, but we can see here the final received DSCP value ranging from 0 to 62 different possible values, and we can see here that really the routers in the network change the DSCP value, and they are behaving accordingly. But so getting these values 2, 6, 8, somehow maybe they follow some policy. Based on that, it changes the value. So this is with respect to 0, 8, and next slide, 36 and 46. So we can see that the DSCP value remaining the same has a lower probability with respect to being stripped. Okay, next slide. Okay, this is, so we are finding some DSCP value packet drops with certain DSCP value which are non-zero. Okay, this I'll first explain about this plot, then I'll explain the table. That is just one example of this. So this DSCP is the original value that was sent. Okay, the right side which represents 0. Okay, this plot is drawn based on the trace route packets that was coming from different routers. So we are analyzing the ICMP packet which we received from the trace box or trace route. Here the 0 value, x-axis 0 value represents, actually we did the DSCP with non-zero value along with some other tests in the same campaign. For example, some TCP option, UDP, and other protocols we run on the same campaign. So basically 0 represents it does not drop, but this is they dropped because of some other reason. So what we can see here, when we analyze the ICMP packets that we received, this y-axis represents from which TTL I received the packet. So after that, there is a modification. So for example, 0 is changed to 2. So at particular TTL, like a 10th TTL, we saw the packet change. So we can see another thing like 0 is changing to 2, 2 is changing to 0. So basically what it says that on 10th TTL, the value 0 became 2. Then after like 18th TTL, for one example, 18th TTL, it became to 0 again. So that means some devices in the network, they are behaving like this. That means it's the same value may not, if you are seeing that same value at the receiver side, maybe it is changed and again read it into 0. So like that, this is that is a non-drop case, but a drop case, these are the right side is the drop case. So for example, when you transmitted like 46, the 0 here TTL is 0. Why I wrote is that 40, because what we saw that when we send a packet with the 46 DSCP value, the first gateway responded with the ICMP. This is ICMP in the payload, the value was 40. So that means there is a box in between from the client device to the gateway, which modified to the DSCP value, the DSC value. So like that, we can see, and we can see that okay, this is about the DSCP change, but the first upper table that represents one example of such case, for example, any packet that transmitted from Oregon to Malaysia, so we saw that CS1, which is actually DSCP value 8, and that is dropped in Amazon cloud because one server belongs to Amazon. Then another example, like Norway, from Norway to Malaysia, we can see A42, it changed to 4 in Telenet when it was going out of that ISP. Then when the DSP value 4, it again dropped by the Temnet Telecom Malaysia. So what we can see that A42 changed to 4 and EF changed to 6. So based on some policy, according to the DSP policy. Yes, next slide, please. So this was, okay, this is the analysis. What we see is when we received the ICMP error message, time exceeded error message, we saw what is the dips of code point in the ICMP message and what is the payload contents, what a DSC value. So for example, x-axis, the big number 2 represents in the payload what is coming, and what the value, the smaller value represents the value that is in ICMP header. So basically, the question comes how they are related. Is that any correlation is there or not? Is like the ICMP error message, the payload, the routers just copy that content, or they follow some kind of rules. So that we are curious to know. But we don't see any. We need to analyze more. This is the preliminary data, so we need to think of more. Next slide. Yes. Okay. This is corresponding to 36, 8, and 10. But we can see that if the payload data is 10, but the ICMP is coming at 0, that means they may not follow the not copying. So some case. Next slide. Next slide, please. Yes. It's before one slide. The previous slide. Yes, yes. So why it is very curious to see, what I see is that this is the last column that represent the ECN. So when the particular router send the ICMP error message, the payload contains corresponding ECN, but the ICMP header message contains either 0, 2, 3, or 48 is the DSC value plus 2 is actually represents the ECN bit, the 2 bits. So here we can see that if the payload contains ECN, but the ICMP header, still it contains a CE bit enabled. That makes things like maybe they are copying or they are following some kind of a policy that, but this gives us some kind of that at least it is copied. We think like, okay, if it is copied, maybe because the packet came to up to that with that, let us say, ECN bit enabled. So it understands that if it comes, it may pass further. It can go return path. So that's why maybe they are directly copying and sending. Yes. Next slide, please. Yes. So this is about that was all about the DSCP code point, and this is about evil bit. So we saw like evil bit. Most of the only 36 drop we have seen, but rest at least the evil bit passes. But so what we can see, what we see is that most of the time evil bit passes successfully, and we did not see it is stripping or it is becoming 0. But in our previous work in the paper NRW, we saw that exceptionally some places it became 0. So, but we can see that most of the cases the evil bit become consistent. So it does not change. So that makes like, okay, previously nobody discussed about like evil bit experiment. So we thought, okay, evil bit is becoming more stable. So the question is how to use that bit like that. Okay. Next. Yeah, that's.
Yeah, thank you. The question how to use this bit is not what we answer today here. Thank you for your data. Yeah, one question.
I have a proposal for our working group policy.
Yes, another thing I want to say. Yes, sorry. Why I'm saying that we saw some DSCP packets with a certain DSCP value the packet drops on the internet. So, which is a bad thing. So, so that's why you are suggesting if the packets with certain DSC value, if it drops, can we follow a fallback mechanism or not? Like that. Yes. Thank you.
I propose that future presentations in this working group, if they have IPv4 only data, must include this sticker in their presentation slides.
And it's a research group as well.
Yeah.
So,
Last second, a future policy might be that we leave a bit more time for discussion. I really liked all of the talks, and I wish we could have talked more about them.
Yeah, so
this is 2 sessions in one, basically, in terms of content.
We had the experience that sometimes there are just no questions, so we have time for questions, but no questions are asked, and we have to deny another presentation, even so there's no question asked. But we have to figure out how to run this in a perfect mode.
I think it means that I should leave 20 minutes.
We could be in the bar drinking beer if there's no questions. So it's a win-win. Right? It's like...
We're trying still how to get this right.
So,
Yeah.
do you have a question about this?
I'll just jump. Just checking. You send ICMP packets and TCP SYN packets.
Yes.
No UDP packets.
Sorry?
No UDP packets in your tests.
No UDP. We tested with the TCP packet.
Okay. I suggest that for the next version. It will be fun to see the difference, if any.
Yes, because we got like suggestion like we could test with his TON packet directly to see the same behavior or not.
How many vantage points did you have that were inside of enterprise networks?
Sorry?
Enterprise networks, corporate networks. Were you measuring enterprise firewalls at all, for instance?
Okay, I tested those things from some different like places like airport or cafeteria,
So you were
or in shopping mall.
And on public APs or something like that, connecting to measurement infrastructure.
So
Yeah.
to my understanding, this is like an initial study. You're planning
Yeah.
to run more measurements.
Yes. Okay. I can say some little bit about our future plan. So what our main goal is that, so the main goal is we are going to make a big measurement platform where anybody comes with new strains or invent a new protocol, then they can deploy it and do the test. So basically, this DSCP test is one of the example from our goal, in our goal.
All right. Thanks, Runa. Let's close up the meeting. I know
Lars
we're
maybe
late,
wants to say
we're
something.
late already. Well, I was going to say on Lars' behalf, the open meeting is tomorrow at 10. So
It
we have
is.
the 2 a.m.
Lars, yeah, come to the IETF open meeting. We have 2 good talks, one on quick security and one on IPv4 Anycast, I think. But that's not actually why I'm here. So another thing is that you guys have been meeting now a couple of times, and at some point I need to decide whether we're chartering this formally as a research group or not. So if you have thoughts about that, you in the audience, send me email or find me and talk to me. If you were me, would you charter this group formally? That's kind of give me an answer.
And assuming that we are continue this work, I would really like if you have data, let us know, or if you want to present something, or also if you have questions and you would need data from somebody else, please let us know.
No, that's it. Thanks so much for being here.
Thank you.
Switch those around.